In this next video on the roller coaster chapter, we want to look at the concept of apparent weight. Apparent weight is the weight that you feel that you are experiencing when you are accelerating. Now, we've got to talk a little bit about the idea of weight. We remember from earlier in the course that weight is the force of gravity on an object. However, that is not what we feel as weight because of the way that we experience the world. Think about a time when you were falling. If you were falling, do you feel like you weigh anything? And in most cases, I would hope the answer is no, that you actually feel as if you are weightless. So when you have just the force of gravity pulling on you, you feel weightless. But what we feel as weight is therefore something else, and that is actually the normal force that is pushing against us. This is actually even the way that a scale works. When you stand on a scale is reading the amount of force that it is pushing up on you. So, and what we experience as weight is the force that's on us from the ground or whatever we are sitting on, standing on as our weight. So, if you think of a free body diagram of someone standing still, you have force of gravity down, force normal up. These two are equal, so our force normal up is our force gravity, and that's why we use scales this way. It actually tells us the force normal, but since we're not accelerating, it is the same as our actual weight. But when we start to accelerate, and one of these forces is larger than the other, giving us a net force, we'll start to see this normal force change, and we experience a weight that's different than when we are standing than our actual force of gravity. So if we were falling with nothing touching us, we'd have the force of gravity down, no force normal up, and we would experience a weight of 0 because there's no force normal. If we were to accelerate upwards, this normal force would be more than the force gravity. So to go about solving apparent weight problems, they're actually Newton's law problems. We'll draw the free body diagram and we'll set F net equals ma. So when you think of F net, Newton's second law, equals ma, F net is the sum of all forces equaling ma. So if you know the acceleration of the object, up or down, and we're going to make direction is very important when doing this, because we're going to have two directions usually. So one up, one down. We can make one direction positive, one direction negative. So when we sum forces, we'll have one positive, one negative. These cancel each other out. Being equal, the net force would be 0, the acceleration would be 0. But if the acceleration is greater than 0, they will no longer cancel each other out. I think the easiest way to really go through this and define it for you is to do some example problems. One of the key examples that's used in apparent weight is standing on a scale in an elevator, because an elevator accelerates you up and down, and you can actually very visibly see the way that your weight is changing. As a bonus points for this course, I am offering, if you would like to do the same experiment where we are standing on the scale in an elevator. If you would like to do this on a larger elevator than what we have, the 3-story ones we have at school, at least a 6-story elevator, you can do this for bonus points. The way this would work is to stand on a scale that is got a dial, not a digital scale, so you can actually see the dial moving. Stand on that scale, videotape the dial of the scale as you go up and down an elevator of at least 6 stories. Bring me a copy of the video or email me a copy of the video to receive credit. Now, let's look at some example problems. An elevator has an acceleration of 3.2 meters per second at the bottom floor and 2.5 meters per second. This should be at the top floor. That's a typo. Can't have two different accelerations in the same place. The top floor. What does the scale read for a 75 kilogram passenger when, in this case, well, the elevator starts up from the bottom floor? So with these, we want to draw like free body diagrams. We have force gravity. We have force normal. I'm going to make up positive for all of these. I can figure out my force of gravity. My force of gravity is going to be 75 times 9.81. Mass times 9.81. Which will come out to 735.75. I want to figure out what this force normal is. So I know F net equals MA. So F net will be the normal force plus, since this is down, negative 735.75 equals 75. This is accelerating upwards from the bottom floor, so positive 3.2. So 75 times 3.2 gives me 240. So the force normal minus 735.75 plus a negative is the same thing as minus equals 240. Add 735.75 to both sides, and I get 975.75 newtons. So the normal force going up needs to be larger than the gravitational force going down, so it feels like you weigh more. Now let's look at the next case. An elevator stops on its way up to the top floor. Remember, at the top floor, the acceleration is 2.5. So in this case, once again, force gravity, force normal. Remember, our force gravity is 735.75. I'm making up positive. In this case, the acceleration will be down because it's slowing down while going up. So the acceleration has to be down, so it will be 2.5 going down. So F net equals ma. So the force normal plus negative 735.75 equals 75 times negative 2.5. It's negative 2.5 because it's going down. So 75.2 times negative 2.5 gives me force normal minus 735.75 equals negative 187.5 newtons. So we'll add 735.75 to both sides, so negative 187.5 plus 735.75 gives me 548.25 newtons. So this person feels as if they weigh less when they are stopping going to the top floor, because the acceleration is down, so gravity has to be larger than the normal force up. Now, starting down from the top floor, I'd like you to try this one on your own. Set up your piece of paper with these next two problems into 4 boxes. So problem 3, problem 4, your answer, my answer, your answer, my answer. So start by doing your answer, then press play again and put any corrections for my answer on the other side. Or if you just got it correct, which would be great, just put correct over there. Okay, so press pause here, try it yourself, and then press play again. Okay, so the free body diagram, force gravity down, force normal up. This is 735.75. We're making up positive. The acceleration is 2.5 down. So this is going to look very similar to the last problem. We're starting down, but our acceleration is the same in the same direction. So force normal plus negative 735.75 equals 75A. A in this case is negative 2.5. So force normal minus 735.75 equals negative 187.5. Add 735.75 to both sides and we get 548.25 newtons. Okay, we're stopping now at the bottom floor. Once again, press pause, try it yourself, and then press play again. Okay, start with a free body diagram. Force gravity, force normal. In this case, the acceleration, because we're stopping at the bottom floor, will be up 3.5. We know this is 735.75. So F net equals ma. Force normal plus negative 735.75 equals 75 times 3.5. or sorry, it's 3.2. 3.2 here. So we get 240. So force normal minus 735.75 equals positive 240. Add 735.75 to both sides, and we get a force normal of 975.75 newtons. One thing we're going to find with elevators is there's 4 possible cases. We're moving, starting up, stopping on the way up, starting down, stopping on the way down. We do this. The acceleration starting up will be positive, stopping up will be negative. If we make it up positive, here I'm making up positive. Starting down will be negative, stopping down will be positive, which means the force normal or parent weight will be greater than force gravity, less than force gravity, greater than force gravity. So that can help you to make sure that you're checking yourself and doing it correct. That only fits if we're making up positive. If we make up negative, then the accelerations would all flip. Our force normals would be a greater negative value than the positive value, and vice versa. One last problem. Now to tie this back to roller coasters. A 75 kilogram passenger is at the top of a loop on a roller coaster, traveling at 15 meters per second. So we're up on top of the loop, the roller coaster car is upside down. The free body diagram here, let's think about it. We always have gravity pulling down. Now which way is the car going to push on the person? Well, the person's sitting in the car, so the car is also going to push down. I'm still going to make up positive here. Now, to figure this out, I need F net equals ma. So force normal plus force gravity equals 75 A. Now I need to figure out some of these values. Force gravity, 75 times 9.81, which once again is 735.75. So force normal minus 735.75 equals 75A. Now I need to figure out what A is. Remember, A, or circle, is V squared over R. So we can solve for that. 15 squared divided by 16, which comes out to 14 meters per second squared. It's accelerating towards the center of the circle. The center of the circle will be down this way. So the acceleration is down. So force normal minus 735.75 equals 75 times negative 14, which is negative 1,050. So force normal minus 735.75 equals negative 1,050. Add 735.75 to both sides, and the force normal is negative 314.25. So it's pushing down at a lot less than normal gravity, so you feel like you weigh a whole lot less. One thing you'll find is if this acceleration gets to 9.81, this force normal will be 0 and you will feel weightless. So if the force going down, the acceleration going towards the center of the circle going down is 9.81, the force of gravity, all of that force comes from the force of gravity. You don't need any normal force. So force normal is 0 and you feel weightless. So we'll use this to do a lot of problems, now that we know circular motion, to find the forces that are on people at all points in a roller coaster.